In this video, we're going to discuss E2 elimination reactions. Our learning goals are to predict the products of an E2 elimination reaction, to draw the curved arrow mechanism for an E2 elimination reaction. Think about the stereochemical outcome using FMO analysis, and to predict the relative rates of E2 elimination reactions. So I guess we better get started by figuring out what an E2 elimination reaction is. So we know that there are two main groups of reactions to alkyl halides. They're substitution and elimination. And we'll be discussing elimination today. So elimination involves removing a hydrogen from the beta carbon of an alkyl halide, in addition to breaking the carbon-halogen bond to generate an alkene, a leaving group, and then the conjugate acid of whatever base you used. Now, it's important to note that just like substitution can occur by two different mechanisms, elimination can occur by two different mechanisms. And we're just talking about one of those today, and that's E2. So today, E2 elimination. So let's get to it. So we have already discussed actually the bimolecular elimination or E2 step. This is thankfully a single elementary step. All right, let's take a look at this E2 elimination. So we're given the products for this reaction. We want to identify the nucleophile and the electrophile, label the HOMO and the LUMO, and provide a complete curved arrow mechanism. Let's provide the complete curved arrow mechanism first. So I've called this the alpha carbon, the one that's bonded to the halogen. Adjacent to it is the beta carbon. So let's go ahead and label those carbons in the product. Let's think about what bonds are made and broken. The beta carbon hydrogen bond is clearly gone, and the carbon bromine bond is gone. We have bromide as a leaving group. And it looks like this hydrogen is in water now. All right, so let's draw the curved arrows. So we're going to have a lone pair on hydroxide, which is acting as a base, except the proton from the beta carbon. Now the electrons in that bond, they come down and make the alkene, the double bond between between the alpha and beta carbons, and then that breaks the carbon-bromine bond, generating bromide. So those electrons end up here. All right, a nucleophile and electrophile, well, that's a little bit tough with an E2 elimination, but we do have the base, and it's our electron-rich species. The alkyl halide is our electron-poor species. And then we have our alkene. Now, this reaction does occur in a single elementary step, but there are two important orbital interactions that we can consider. We discussed that the non-bonding pair of electrons on oxygen attack sigma star CH, which is being represented by this arrow right here. And then we also have these electrons in the sigma bond here attacking sigma star CBr. So we can draw out both of those interactions, and they'll look like this. We'll draw them out here in the bottom of the slide. So here's sigma star CH, and it's empty, and it's going to interact with the non-bonding electrons on oxygen. Right, so that's our first interaction here. Okay, and so now we're going to have our second interaction. Let's change colors, and that will be the sigma CH electrons. This time that is the filled orbital interacting with, so here we go, sigma CH. And that's a bad place to put that. Let's put it over here. It's going to interact with sigma star CBr. And in order for those two orbitals to interact, they need to be aligned. And the way for them to be aligned is if the beta carbon, this beta CH bond, and the alpha CBr bond, their relationship in space is called anti-periplanar. So you would imagine if you look down this alpha beta bond, what you would see, if you drew a Newman projection, will look like this. Well, let's not worry about the other substituents, but here is your leaving CH bond that's being deprotonated and your carbon leaving group bond. They have a 180-degree dihedral angle, and so that makes them anti-periplanar. Anti means 180-degree dihedral angle, and then the periplanar means that they're in the same plane. Okay, that's fun, right? It's your turn now to be sure that you understand what we've been discussing. So go ahead and generalize the pattern represented by this E2 elementary step. Label as much as you can, draw the curved arrows, and then we will discuss. What I really want you to be able to do as starting place is to identify the alpha carbon, identify the beta hydrogen, and be able to draw the curved arrows. So we have the lone pair on oxygen attacking sigma star CH. So donor, filled, empty. Those electrons make this double bond here between the alpha and beta carbons that we see in the alkene product. And then when you do that, you're filling up sigma star CBr, right? You're having the sigma electrons attack sigma star CBr. This is how that pi bond is formed. And the sigma CBr bond breaks. And then those electrons that were in the CBr bond, they end up with bromide. Okay, so here's our leaving group. A couple of points that I want to make here before we move on is that the hydroxide, the base, it needs to be strong. So a strong base is required for an E2 elimination. And it needs to be really as strong or stronger than hydroxide. So think about, well, how can we think about the base strength? Well, let's think about conjugate acids. So the conjugate acid of hydroxide is water. We see that it's formed in this reaction, right? And we want to think about its pKa. So the pKa of water is 16. So we need bases that have conjugate acids with pKa's greater than 16. And they will be good bases for the E2. So I'll give you another example. Amide, this molecule, it is a good base in the E2 because the pKa of its conjugate acid is 35. So the super weak acid makes for a super strong base. And then there are other examples as well. But a strong base is required for an E2, and you can evaluate that with the pKa's of its conjugate acid, which you've memorized. That's why I make you do it, because it's useful to have this data at hand. Let's move on. So let's predict the products that we would observe for each reaction here. So each of these reactions proceeds by an E2 elimination. So go ahead, draw the curved arrows and predict the products. Please pause and do this. Now, a place to start is to identify the alpha carbon and identify the beta hydrogens, because we know that the E2 pattern is elimination of a beta hydrogen and that alpha carbon to generate an alkene between the alpha and beta carbons. So you first just want to identify the alpha and beta carbons. So here are the beta carbons for this first molecule, and they're different, but only one of them has hydrogens, and that's this one that I call beta. Beta prime, there's no hydrogens here, so we're not worried about that. But there are hydrogens, there's 3 of them on this methyl group, this beta carbon. So we would have sodium hydroxide come in, deprotonate, the electrons from that bond make the double bond, and bromide leaves. And that will give us this product. It'll also give us bromide and water. All right, let's take a look at the next reaction. So we would have our alpha carbon. We would have, again, 2 beta carbons. There is a proton on beta prime this time, but when you have the chance to deprotonate an sp3 carbon, that's what you're going to do. And so that's what we do here. So we're going to have this base come and deprotonate the methyl group, and that will generate this diene, or we've made this new double bond here. Right, so we can see we're forming alkenes. These electrons end up forming the alkene. Let's keep trying. Now here's the alpha carbon. I put this molecule in for a reason because I need to introduce what OTS is. OTS represents a tosylate. So this is a tosylate, and it's really similar to an alkyl halide. And so the OTS part, I've represented that up here. The TS stands for tosyl. So let's come back to that in just a sec. Let's look at what happens when we react this molecule with sodium hydroxide. So if the tosylate behaves like an alkyl halide, we're going to expect to see an elimination reaction. These 2 beta hydrogens are exactly the same. So what I mean is these 2 carbons have hydrogens that are exactly the same. There's a mirror plane down the middle. I'm arbitrarily picking one of those carbons to deprotonate. So non-bonding oxygen attacks sigma star CH. Those electrons make a double bond between the alpha and beta carbons and displace the tosylate leaving group. That generates the expected alkene. And then the leaving group, which we would just call OTS, but I'm going to draw it out for you. Okay, so that's the OTS. And then water, of course, which is the conjugate acid of the base. So OTS, it was actually in the SN2 lecture as a really good leaving group. And this is why tosylates behave like alkyl halides, because this is a very good leaving group. I mean, this should look to you a little bit like this species. And what is this species here? Well, that's the conjugate acid or conjugate base of sulfuric acid. So that's a super stable base, right? And so tosylate's pretty stable too. Its conjugate acid, because we said if we wanted to evaluate leaving group ability, we should look at the conjugate acid. Its conjugate acid, tosic acid, has a pKa of about -6. Oops, let's write that again, -6. So what that tells you is that tosic acid is a strong acid, and that confirms for us that tosylate is a really good leaving group. So we're going to talk a lot more about tosylates, but for now, it's a good leaving group, and if you have a tosylate, it's going to behave like an alkyl halide, and you're going to get an E2, which is what we had here. All right. Let's try our last example. In our last example, we're back to alkyl halides, and we have a primary alkyl halide, and it has 1 beta carbon. Yeah, I wasn't talking about substitution pattern here, but we are going to get back to thinking about that later. So this is a primary alkyl halide. And now we have potassium T-butoxide. So potassium T-butoxide here is a strong base. It's great for E2. We can think about the conjugate acid of sodium T-butoxide. It's an alcohol, so it has a pKa of about 16. So that tells us conjugate acid strength 16 and greater will be a good base for E2. So T-butoxide is a good base. I'll leave it at that. And then from here, we're going to see it deprotonate the beta carbon. So let's go ahead and show that. So we're going to have T-butoxide deprotonate those electrons are going to come down and displace bromide. A little bit awkward on the curved arrows, but you've got it. And there's our alkene product. We will also have T-butanol, the conjugate acid of the base, and the leaving group, bromide. But typically we care about the organic product. When I ask you these questions on exams, I'll ask you for the single major organic product. So we really care about these species here. Excellent. All right, let's move on. So what is the rate law for an E2 elimination reaction? This is our prototypical E2, or it's the example that I gave you at the beginning of this class and in our class on FMO analysis of elementary steps. So what is the rate law for an E2? Well, the rate is little k times the concentration of the alkyl halide times the concentration of the base, right? We only have this single elementary step, so by definition, this is going to be the rate law because both of these species are involved in that one step. This is called an E2 because it's second order, right? You have two first order species for a total of a second order rate law. So both the alkyl halide and the base will affect the rate of this reaction. And we can think back to what factors affected the rate of SN2 reactions. For an E2 reaction, we really want to think about leaving group, which is part of the alkyl halide. The leaving group affects the rate. More stable leaving group, faster rate of reaction. So weaker base, faster rate of reaction. And we evaluate base strength through conjugate acid strength. Also, the stronger the base, the faster the E2. Okay, so those are the two main factors that we'll focus on in this class. So here's an example of an E2 reaction, and I would like for you to draw the curved arrows for this reaction. Well, we can see that we're breaking this bond. We're breaking this bond. This is our alpha carbon. Here's our beta carbon. Alpha, beta, right? I can tell that this is the beta carbon because it's bonded to methyl and phenyl. So I'm using the substituents in the molecule to guide my assignment of the different carbons. And then I can see I have sodium ethoxide. So this is an alkoxide base. And alkoxide bases, just like we saw sodium T-butoxide or potassium T-butoxide in this previous example. Alkoxide bases are good bases for E2. All right. Sometimes you'll see the conjugate acid as the solvent. Ethanol is the conjugate acid of sodium ethoxide, so don't be surprised if you see that. So let's show what happens. So sodium ethoxide, it's a strong base. It is going to deprotonate the beta hydrogen. Those electrons come down, and we end up with the organic product shown, the bromide leaving group, and ethanol. All right, easy peasy, right? Well, we're going to think a little more deeply about this example. There are actually two possible alkene stereoisomers from this reaction, but this is the only one observed, the one that we examined on the previous slide. So how can we explain this observation? And then also, first of all, how are these two molecules different? Well, this is the Z isomer, and this is the E isomer, and the E is not observed, right? These are stereoisomers. And so because we have only one stereoisomer formed, this is a stereoisomer. selective reaction. In fact, this is stereospecific, meaning that different diastereomers of the alkyl halide will make different diastereomers of the product. And we can think about that a little bit more if you like in a minute. But for this example, this diastereomer, right, there are two chiral centers. It makes this diastereomer of product. So let's go ahead and look at that. We've already drawn the mechanism. We have ethoxide deprotonating the beta hydrogen and then bromide leaving. But in order to explain why only the Z isomer is formed, we need to remember that this requires anti-periplanar alignment of the beta CH and the alpha CBr bonds. And we have drawn this picture before, and we're going to draw it again and again and again. This time in a slightly more complicated example. But this is required because the electrons from sigma CH, they are filling up sigma star CBr to break that bond. So that we have our filled orbital, filled sigma CH. Those electrons are filling up sigma star CBr. It's empty, it accepts the electrons, and filling up that antibonding orbital breaks the bond. In order for this to happen, these orbitals must be aligned. So the orbitals must be aligned. And if they're aligned, to be aligned, they need to have this anti-periplanar conformation. So what we can do is draw a Newman projection, which everybody is going to be really happy about. So recall Newman projections from earlier in the class. And this is what the Newman projection would look like in the reactive conformation of the molecule, which is the one that has the alpha CBr bond and the beta CH bond aligned in this anti-periplanar conformation. So this is the one that reacts. This is the one I have drawn right here and right here. And in this conformation, you can see these phenyl groups, they're on the same side of this double bond that's forming between our carbon atoms, which are kind of hard to see, but we have our beta carbon in the front and our alpha carbon in the back. There's a double bond forming between them. And those two phenyl groups, they're going to be on the same side of the double bond. And then the methyl and the hydrogen, they're on the same side. And then you can see that in the product, right? Here's the phenols, they're on this side. That's why this is a Z isomer. And the methyl and the hydrogen, they're on the same side. Okay, so we're seeing this relationship with the methyl and the hydrogen forming here, and this relationship with the two phenols forming here. So only one stereoisomer of the product is formed because of this requirement for the anti-periplanar alignment of the beta CH and the alpha CBr bonds in order for them to overlap. Now, so that's an anti-elimination. E2 reactions, by and large, they go by anti-elimination, almost always. But we can ask the question, is a syn elimination reaction possible? And I want you to think about that. This is the same alkyl halide that we examined here. So we already know what product it makes, right? When it is treated under E2 conditions with a strong base, sodium ethoxide, we know that it's going to form the Z product. We already know. This is what's observed, and this is from the anti-elimination. Okay? But we still are trying to answer the question, what would be the product of a syn elimination? So the observed product, from the anti-elimination, it comes from reaction in that conformation. If we want to know, well, what would we get possibly, I don't know, just do blue, from a syn elimination, we need to rotate and get into the syn conformation. So let's do that. So we're going to rotate here. And we're going to get the carbon-bromine bond and the carbon on the beta hydrogen bond in a syn conformation. And so syn has a 0-degree dihedral angle. This is what syn means, and that's why I have that written at the top here. I'm going to grab bromine and pull it down. And so what we're going to see here, I'm going to keep that front carbon the same. I keep the beta carbon the same. That's the one that I chose to put in front. And then in the back, that's the alpha carbon. Now bromine is down here. And that would be our hydrogen, and that would be our phenyl. All right, so now we have these two bonds in a syn relationship where there's a 0-degree dihedral angle. In other words, they're eclipsed, right? So from here, we actually could have elimination, perhaps. All right, there we go. And what would that get us? Well, if we had elimination in this conformation, we would have phenyl and hydrogen on the same side of the alkene, and we would have phenyl and methyl on the same side of the alkene. So we would get something that looked like this, phenyl and methyl on the same side, and phenyl and hydrogen. So let's do some highlighting. So same side, phenyl and hydrogen. Same side, phenyl and methyl. And so this was the E isomer, right? This was the E stereoisomer right here that was not observed. So what do we learn here? Well, we learn that syn elimination is not observed, anti-elimination is observed. All right, so once again, anti-elimination is observed most of the time for E2 eliminations. And that's why for this molecule that we've been examining, we saw only this product that occurred through this anti-elimination. Now we thought about what would happen if a syn elimination occurred. If it did through this conformation, so this would be our syn conformation, it would have made the isomer that was not observed, the stereoisomer, the E isomer, okay? So that's kind of how we know it doesn't happen, because we don't observe the E isomer. We don't observe the product of syn elimination. So there's this question that I ask here, do syn eliminations ever occur? Well, we need a cleaner slide, so let's think about that. So we know it didn't occur for this molecule because the anti-conformation was easily accessible, and that one is lower, the anti-elimination is lower energy. So not for this molecule, because the anti-conformation was easily accessible. There was free rotation around this bond. It reacts through the anti-conformation. But for some molecules, the anti-conformation is not accessible. And when it's not, then you might see a syn elimination. So let's look at that. I can show you an example. So we have this bridged bicycle. This is a bicycle, means there's two rings. And there we have a carbon-bromine bond. So that's our alpha carbon. This is our beta carbon. If we were to treat this with sodium hydroxide, we would be able, and we probably have to heat it, because it's going to have a little bit higher activation barrier, because this is going to proceed through a syn elimination. We will see an alkene product. So we will observe E2 here. And that's because sigma CH is aligned with sigma star CBr in this syn conformation. I can tell this is a syn conformation. If I looked down the bond, I would have hydrogen and bromine eclipsing one another. And there's the ring. Yay. All right, so that I see that they're aligned. It's just that the overlap is not as good because you have the little lobe of sigma CH overlap with the big lobe of sigma star CH. So they're aligned, but the overlap is not as good. So this is just a higher energy transition state. So the bottom line is that it can happen. It doesn't usually. Usually we have anti-eliminations, okay? So we're only going to have a syn if that's the only option. And that is why we saw for this molecule, it only formed the Z isomer because the Z was from the anti-elimination. But here's my question. That's why I have this slide here again. Haha. I want to know, well, like, what if I want to make this? What if I really want to make this? Can I just wish that a syn elimination happens? Yes, but that is not going to help me. Do you remember, probably not, what I said several slides ago? I said that this E2 elimination was stereospecific. Different diastereomers of the alkyl halide gave different diastereomers of the alkene. So if I want the E isomer, if we want the E isomer, I know it's not going to happen from this diastereomer because it's the product of the syn elimination, which is higher energy and does not happen, right? So if we're going to draw a reaction coordinate diagram, the anti-elimination, because the orbitals have better overlap, it is lower energy than the syn elimination, lower activation barrier, faster rate. We're only going to see the anti. No problem. If this is stereospecific, just change the stereoisomer. So let's just change, let's make a diastereomer. Let's change the relationship between the phenyl and the hydrogen on the alpha carbon. So let's just use the diastereomer. Okay, so these are diastereomers. Okay, and then let's see what happens. We already have these in the anti-conformation. So right now they're anti to one another. You could draw Newman projection if you want. So we have the anti, alpha CBr and beta CH. So this is the reactive conformation. So we're going to have the base coming and deprotonating, expel, expel. And what we'll have happen is we'll have methyl and phenyl, they're both in, and there they are on the same side. Phenyl and hydrogen, they are both out, so here they are on the same side. So if we use a diastereomer, if we started from this molecule, we could totally make this product because this is a product of the anti-elimination. Super. Guess what it wouldn't make? This diastereomer, it wouldn't make this one because that would require a syn elimination. All right, the past probably 10 or 15 minutes, or we're talking about the anti and the syn. It's super complicated. It's the hardest thing we're talking about today. So you might have to listen to it a few times to get it. And you want to probably prioritize just drawing the products and drawing the mechanism first, and then really try to get down this anti-elimination and all the cartoon molecular orbitals and all of that. At the beginning of the class, I gave you these problems where I asked you to predict the product of the E2 elimination reaction. And I intentionally designed these problems so that there was one major product of each reaction. We're going to look at a little more complicated of an example now. So we're going to look at the E2 reaction of pent-2ene. And it makes a complex product mixture. We have 3 different products shown here. So I would like for you to just start by pausing and drawing the curved arrow mechanism that explains the formation of each of these products. A good place to start is to label the alpha carbon and then to notice that you have 2 different beta carbons. And both of those beta carbons have hydrogens on them. And such, both of them can be deprotonated. So we can see that deprotonating at beta, or C1 here, if we're going to number the carbon chain in terms of nomenclature, which I'll go ahead and do. If we deprotonate at C1, that will give us this product. If we deprotonate at C3, we will get these two products. Okay, if we just look at where the double bond is, we know that the carbon-bromine bond is broken, but the difference is which of these CH bonds was broken. So let's draw the mechanism. We'll start with the mechanism to form pent-1-ene, so deprotonating at C1. So we'll have ethoxide, our base, deprotonate at C1. C1 is beta to our leaving group. Beta just means adjacent to the alpha carbon, the carbon that bears the leaving group, bears the halogen. And then we'll get pent-1-ene plus bromide plus ethanol, which we don't really care about right now. Excellent. So now how do we get to the other two products? Well, again, that is from elimination at carbon 3, which is also beta. I called it beta prime, which just means it's different than the other beta carbon. It's also beta to the halogen leaving group. So this time we'll have the base come in and deprotonate, and the bromide leaves, and that will give us both of these products. Well, it's like a little maze. Okay, that'll give us these products here. Cool. And let's go ahead and name those two products. So we have trans-2-pentene and we have cis-2-pentene, or pent-2-ene by the new IUPAC rules. Sorry about that. Awesome. So what did we learn from this? Well, we learned that when there are two different beta carbons with beta hydrogens, multiple products might be observed. However, we can see that these products are not formed in equal amounts, right? So we have much more of the elimination at C3 than we do at C1. So let's try to understand why that is and think a little about that a little more deeply. So we can think about thermodynamic conditions versus kinetic conditions. So in a reaction that's under thermodynamic conditions, the lowest energy product is observed. You know, and it might not be exclusively formed, but it's favored. Under kinetic conditions, we have the product formed by the lowest activation barrier as the major product. So and these can be the same product sometimes, but let's just look at this. So if we have two possible products, here they are, A and B. B is lower energy, so B is the thermodynamic product. Okay. But let's say that somehow A is formed by a lower activation barrier, right? So you can see A is formed by a lower activation barrier. That would make A the kinetic product. So I would like to answer the question, do you think that this reaction is under thermodynamic or kinetic conditions? So what do you guys think? Is it under thermodynamic or kinetic conditions? Well, you need to think about what is the relative energies of these products. So we can see that these products, the pent-2-enes, they're disubstituted alkenes, versus the pent-1-ene, That's a monosubstituted alkene. So which one is lower energy? The disubstituted or the monosubstituted alkene? You're right, it's the disubstituted alkene. They are lower energy due to enhanced hyperconjugation between the alkyl substituents and pi star CC. So if you'd like to review that, you can go back to that lecture and review it. But this is the lower energy alkene, and we have more of it. Thus, yes, this reaction is under thermodynamic conditions. We see the lowest energy product form. We still see a mixture, but the major product is the lower energy alkene. And then among the cis and the trans, which one is lower energy? Just to review, the trans is lower energy than the cis, and we do see there is more trans than cis. So that also confirms that the reaction is under thermodynamic conditions. Well, what if you wanted to make the monosubstituted alkene? How could you do that? Well, let's think about that question a little bit more. It turns out base choice can affect the distribution of products, and we'll think about how the base choice will do that. Examine these reactions, get oriented. All right, we can see that there's two products of these reactions. So it's the same alkyl halide. What we're changing is the base. So we have potassium ethoxide versus potassium T-butoxide, getting the same two products. But with potassium ethoxide, you have 71% of the tri-substituted alkene, which involves elimination at the secondary carbon right here. Versus for potassium T-butoxide, you have 72% elimination at this primary carbon. And the more substituted product is definitely the tri-substituted, and it's lower energy. It is definitely the thermodynamic product. But what you can see when you use potassium T-butoxide, you can favor the less substituted product, favor the higher energy product. Well, how do you do that? Well, essentially, you're putting this reaction under kinetic control. Let's think about the difference between potassium ethoxide and potassium T-butoxide. And the big difference is just the steric profile of the base. So here is ethoxide. Here is T-butoxide. And I think even when I draw them out like this, I'm really not doing justice to just how huge, we'll call it bulky, how bulky T-butoxide is. And so when we think about the two protons, the two different beta protons, we really need to consider how easy it is for a base to reach those protons. So deprotonating at this secondary beta carbon, so this one here, it does lead to the more substituted product, but it's harder to reach that proton because it's secondary and you got to get in there around that methyl group and deprotonate. So for ethoxide, that's no problem. We can call ethoxide slim. It's no problem. It can get in there and deprotonate it and make the lower energy product. So I've represented that with this reaction coordinate diagram. Definitely a little bit higher energy probably to reach that more hindered proton, but it doesn't really matter. Overall, we observe the major product is the lower energy one. Versus when you bulk up the base, now we have a really bulky base. T-butoxide now is so bulky that when it tries to get in here to deprotonate that secondary beta hydrogen to make the more stable product, the transition state is just much higher in energy because it is clashing with the alkyl chain. It's too big. It is much easier or a lower energy transition state for it to deprotonate at the primary beta carbon, forming what we observe as a major product for the E2 elimination here with T-butoxide. So for the sodium ethoxide, which is slim, it can get in and deprotonate that secondary beta hydrogen to generate the more substituted product as the major product. We would say it's under thermodynamic control. It favors the lower energy product. Meanwhile, T-butoxide is just so bulky, so big, that to form this lower energy product, the activation barrier is just much higher than it was for ethoxide, since T-butoxide is so much bigger. So because there's that high energy, high activation barrier, we do favor the less stable product with the much lower activation barrier. It's just a much lower activation barrier to form the higher energy product. And that is because T-butoxide is bulky. Okay, bottom line, if you didn't understand any of that with the transition states and kinetic versus thermodynamic, you need to know with a bulky base, you can favor formation of the less stable product, and that's that, okay? So if you're doing an E2 with a small base, so ethoxide or hydroxide, you will favor the thermodynamic product, so the more substituted product. If you use a bulky base like T-butoxide, you can favor the kinetic product, the higher energy, the less substituted alkene, right? The di-substituted one. All right. Now, other structural factors can favor the less stable alkene isomer. So let's think about how we can explain this data. So we have these two alkyl halides. They are diastereomers of one another. We're treating them with sodium ethoxide. So a couple of things. It's a strong base. It's a good base for E2. And now we know that its steric profile matters, and it's a small base. So it's typically going to favor the most stable alkene because we don't have to worry about being too bulky to get in there and deprotonate. It's usually going to favor the most stable, the most substituted alkene. Awesome. So for this first reaction, we see that that is indeed formed. This is tri-substituted, and it is certainly more stable than a di-substituted alkene. These two products are constitutional isomers. The tri-substituted alkene is formed from deprotonation at this tertiary beta carbon to break this bond, and that forms a tri-substituted alkene. The di-substituted alkene is formed from deprotonation at that secondary beta carbon to form the less substituted product. So we have the same base, so this is not a base choice issue. It really has to do with the stereoisomer. The key here is that these are diastereomers of one another. So we need to be thinking about that, about their spatial arrangements of the atoms in order to explain why one of them reacts by E2 to form the more stable isomer, and while the other forms the less stable. Now these are cyclohexanes, so guess what, guys? We need to draw the chairs. I already did it for us, so here they are. We already know that the tertiary beta carbon, so this one, is going to be the one that's deprotonated, but we still want to go through the motions and look for the carbon hydrogen bond, this anti-periplanar to the leaving group. So right here, this is our carbon leaving group bond, and in this chair conformation here, we do not have a beta hydrogen bond that's anti-periplanar. None of those are anti-periplanar to the carbon leaving group bond. So let's look in the other chair conformation. So here's our carbon leaving group bond. Let's draw in all of the beta hydrogens and look for one that's anti-periplanar. Well, you actually have two. You have this one and this one. They're both anti-periplanar to the leaving group. Now, Deprotonation of this hydrogen, it forms the trisubstituted alkene, the one that's observed as the major product. Deprotonation here would form the disubstituted, which is not observed for stereoisomer A, just because that forms the less stable product, and this seems to be under thermodynamic control. So we see elimination at the tertiary beta carbon to form the more stable product. Okay, cool. That's what we would expect. Now, why in the world doesn't this happen with stereoisomer B? Why do we not just form the more stable product? Well, let's figure it out. Okay, so I've drawn both chair forms. Let's draw in all of the beta hydrogens, and let's try to find one that is anti-periplanar to the leaving group. So here's the carbon leaving group bond. We're not sure which chair it reacts from. Okay, so it looks like the only anti-periplanar carbon hydrogen bond I can find is in the chair form. This is certainly the less stable chair, but this is the one it reacts in, and that's fine. That is the only anti-periplanar hydrogen at all ever to that leaving group. So that's the one that's eliminated. And that does form the less substituted product. So the less substituted product is formed because that's the only anti-periplanar hydrogen that we had. And that's where we have the best orbital alignment, when we have an anti-periplanar beta hydrogen to the leaving group. And so that's the product that we form. Well, it has been an epic journey, but I think we've made it. So can we predict the products of E2 elimination reactions? We can. We're going to recognize them because we're going to have an alkyl halide or a tosylate, and we're going to have some strong base. We're going to identify the alpha carbon. We're going to identify the beta carbons, and we're going to deprotonate them. For this example, I've given you beta carbons that are the same. So we just choose one, and you're going to get the alkene, the leaving group, and the conjugate acid of the base. Hey, look, we just achieved our second learning goal, providing curved arrow mechanisms for elimination reactions. There were a few tricks, right, with predicting the products. So generally, you want to think about forming the more stable product, so the more substituted alkene. And we saw except in two cases, when you have a bulky base, like in this example, when reaction with potassium t-butoxide did favor the less substituted alkene. And then the other exception was when it's just not possible to find an anti-periplanar hydrogen to the leaving group. And so the example was here. For this molecule, diastereomer B, there just wasn't an anti-periplanar hydrogen on that tertiary beta carbon. And so you didn't form the more stable product, you formed the less stable product. And that's a super hard question. It's one of the hardest ones you're going to encounter. So if you didn't quite get it, we're going to save it until you have some spare time to think about it and focus on other things for now. All right, explain the stereochemical outcome of an E2 elimination reaction with FMOs. You can do it, right? So really the key is that sigma CH has to be aligned with sigma star CX. That's the key. And that's why we have this anti-periplanar, or as a worst case scenario, the syn periplanar examples that you can go back and look at. And then finally, predict the relative rates of E2 elimination reactions. I didn't give you any practice problems for that, but I did tell you what I want you to think about. I want you to think about base strength. So the stronger the base, the faster the E2. The slimmer the base, the stronger the E2. And I want you to think about leaving group. So more stable base is a better leaving group. So thinking about X minus. If it's more stable, it's a better leaving group. All right, you guys can do this. It takes practice. It takes being organized. So get to it.